Hi guys, this is Jojo. Today I'm gonna share with you guys one of my favorite problems. This actually not in our homework problems, but I think this problem gonna be really helpful to share. So I'm gonna go through it with you guys today. That problem is 6.59 in our textbook, and uh, the question asking us to determine V out at t greater than 0. So I know that that's going to be the step response. But looking at the given op-amp, I have capacitor 1 and capacitor 2. There's no way for me to combine C1 and C2 together because they are not in parallel, they are not in series either. So I know that this is going to be the second order circuits because I have two components that can store energy in my circuits. So to solve this type problem, we need to analyze the circuits at t less than 0 and t greater than 0. At the time frame t greater than 0, we need to consider at t equals 0 the transient state and the steady state, which is t equal infinity. So let's analyze the circuits at t less than 0. So as you can see, I already sketched out the circuits. But well, one more thing, really important, but I forgot. They given V in A U of t. So when I see that, I know that when t less than 0, then U of t gonna be 0, and my V in gonna be 0 volt. When t greater than 0, U of t gonna be 1, and then my V in gonna become 8, and it's actually 2 volt as given. So now when t less than 0, I have no source, nothing. So we don't have anything to try the circuit. So of course, VC1 gonna be equal VC2. Also gonna be the same thing with VL, gonna be 0 volt. So now let's move to the next time interval. When t greater than 0, I like to analyze the circuits at t at the steady state first because at the transient state it's more complicated. So save that to later. So right now at t equal infinity, I know my V in gonna be 2 volts given. And now you can see that when the capacitor fully charged, it's gonna behave like open circuit. So I have C1 and C2 as an open circuits right here. Now we're gonna go ahead and write the KCL, the first KCL at VA. So I have VA minus V in, which is 2 volt, over R1, which is 5,000 ohm, plus VA minus VB over 10 kilo ohm, plus IC2. But now look at IC2. It's open circuit as C2, so IC2 actually 0. So just cross the term out. So now our first equation is complete. Now we're gonna move into the second KCL at VB. I have VB minus VA over R2 plus IP, I call it IP. And this one right here, we know like one of the two really important property of the op-amp, the current flow in the op-amp right here and right here is actually 0. So I know that my IP is 0, so I just plus 0. And right here, IC2, my IC1, it's also 0 because it's open circuit. So see it right here. So by this, I can make a statement that VA equal VB. Now plug it back into this equation right here. And you guys can see that the term right here, VA equal VB, right? So when VA minus VB, it's going to be 0. So the term right here is going to be 0. So I have the first term, VA minus 2V over 5,000, going to be 0. So therefore, I know VA at infinity equal VB at infinity equal 2 volt. Now we need to find V out because the question asking the main character right here is V out. So we need to determine V out at infinity. So let me highlight this node right here. So the virtual short right here. So they actually is VB right here too. So we can say that right here, the node right here is the 2 volt. So I can have the current flow down, the current flow up. This current flow into the op amp is 0. Let's call this one a IR3, okay? So now I'm gonna go ahead and write the equation for the KCL at this node right here, 2 volt, okay? So 2 volt minus 0, so I'm running the current flow down this way, over R4 is 20 kilo ohms plus 2 volt minus V out over 12 kilo ohms is 0. And now I can solve for V out at infinity. When you do the algebra a little bit and solve it out, when you get 3.2 volt. So here's the all of my important value that let's highlight it and save it for later. So now we're gonna move on to the next thing, the most complicated one, transient. So you see I put back everything into the given circuits like the original given circuits. Right here, C2 and C1 just look like C2, just like capacitor. So now I'm gonna write the KCL right here. Let's call it VA and VB again, because we've been calling it VA and VB. Write a KCL at VA. I have VA minus Vin, which is 2 volt over R1. And my R1 is 5,000 ohms plus VA minus VB over R2, and have R2 is 10,000 ohms, and plus IC2. IC2, that current flow through IC2 gonna be C2 dt. Voltage across the C2. Voltage across C2 this time gonna be VA minus V out. This is my first equation in transient state. Let's move on to the second equation. Okay. We're gonna write a second KCL at VB. I have VB minus VA over R2, 10,000 ohms. Plus the current flow in here is still gonna be 0, and the current flow down here, IC1 gonna be C1 dt. Voltage across C1 is actually VB minus 0. Just write VB equals 0. So that's gonna be my equation 2. Next, I'm gonna try to derive a third equation right here, the KCL right here. So because the main character is asking for V out, so we need to write something that involves V out in here. I'm gonna have, let me highlight so you can see where it says VB, virtual short, right here. So this is still gonna be VB. So I'm gonna denote it right here, VB. So my KCL gonna be VB minus V out over R3. My R3 is 12,000 ohms plus VB over R4. My R4 is 20 kilo ohms. And the current flow this way is 0 because it's flowing into the op amps, right? So it's 0. This is my equation 3. So because the main character is V out, so I try to solve for V out. I try to solve for VB in terms of V out, because I just want my ultimate equation is something stick with V out, right? My variable is V out, so I need to solve for other variable in terms of my main variable. Just solving this equation can help me solve for VB in terms of V out. So when you do the algebra a little bit, you can find out V out actually 6.625. No, my bad. I'm sorry. I take it back. Oh yeah, actually it's correct. Gonna be 6.625 V out. Let's call this in my equation 3. Now I want to turn everything into just one variable, because right now I have VA, VB, and VL as my 3 different variables, right? So I'm just gonna try to substitute back. I'm gonna substitute equation 3 into equation 2. So I have 0.625 minus VA over 10,000 plus C1 dt 0.625 VL. And then when I solve it, I'm going to have this equation right here is VA equal 0.625 VL prime plus 0.625 VL. I do have I did work it out before, so I have this no equation right here, but I will post my paper writing, and it's I do extra algebra in there so you can see it if anyone have question. So now I'm gonna sub equation 4 into equation 2 and equation 3 into equation 1. I'm gonna have a new equation. Just you substitute VA, you right here. You can substitute VA in here, and in here. And also you guys can and you substitute VB equal 0.625 VL in here. And let's see what we're gonna get. We gonna get something, after I reduce everything, I'm gonna get 1.25 times 10 to the negative 4 VL double prime. Should I do that, or should I just work out everything, because it's gonna be a long thing? Or maybe just do it, because it's fun anyway. Okay, when I substitute everything in, I'm gonna have 0.625 VL prime plus 0.625 VL minus 2, everything over 5,000 plus 0.625 VL prime plus 0.625 VL minus 0.625 VL over 10,000. This right here cancel out, plus C2 dt 0.625 VL prime plus 0.625 VL minus VL over equals 0. Now, this guy right here, when you distribute inside, you can have VL double prime. This right here can be VL prime. So I think that I almost guess my second order differential equation, right? After you do everything and reduce it, I'm gonna get this guy, 1.25 times 10 to the negative 4 VL double prime, because that term actually the term right here, C2, when I distribute in here, I get this term right here, plus 1.125 times 10 to the negative 4 VL prime plus 1.25 times 10 to the negative 4 V out equal 4 times 10 to the negative 4. I'm going to reduce the first 1.25 times 10 to the negative 4 for every single term. So I multiply both sides by 1 over 1.25 times 10 to the negative 4. So my second order differential equation is gonna look like this. Plus 0.9 V out prime plus V out 3.2. And you guys can easily see that this is A, B, BE1, and this is my C. So now I can determine alpha is A over 2, that actually 1.45 NP over S. My omega naught gonna be B is actually 1 radian per second, and this gonna let me know how damn our circus, right? Because alpha a less than omega naught, so I know that's the under dam. Sorry for my handwriting. I know it's hard to write in here. It don't look good at all. I'm sorry. Okay, so because I know it under dam, so I need to find omega d, which is omega naught square minus alpha square, gonna be 0.9 radian per second. This is radian. I'm sorry. This is radian per second. Okay. So now I'm going to determine D1. D1 actually V out at 0 minus V out as infinity. How do we determine V out at 0? So let's go back to the circus right here. So we know that the voltage across a capacitor cannot change spontaneously. So at T less than 0, the voltage across the C1 right here is 0. And voltage across C2 also 0. So it's gonna take this voltage, go to the initial state at the next time interval, which is T greater than or equal 0. So when at the T equals 0, this the voltage still gonna be 0. The voltage is still gonna be 0, and yeah, we have the virtual short right here, right? So everything right here gonna be 0, and that thing up here is 0. So V out also gonna be 0. I mean V out at time equals 0 gonna be 0. And V out at infinity, we saw it right here, is 3.2. So I have it gonna be negative 3.2 volt. Now we're gonna solve D2. D2, we need to figure out what is V out prime at 0. Now how do we do that? Are we running into an issue? V out gonna be equal 0, right? Now take a look at equation 4. This equation right here that I have. So VA right here, I can solve for V out prime gonna be 1 over sub 5 VA minus VA 0 and V out 0, right? Yeah, so now how do we determine VA at t equals 0? Go back to this circus again. So we have everything in the green node I highlight is 0. And everything in the green node is 0. But actually, VC2 is also VA. So therefore, VA is 0 too, right? So now it's become easier for us because it's 0 right here. This is 0. The L as t equals 0 also 0. So the whole thing right here is 0. So the whole thing right here is 0. So now I have V L prime at t equals 0 is just 0. Yeah. So D2 average right here. D2 gonna be V L prime t equals 0. So that is just 0 plus alpha B1. Alpha is 0.45, and then our D1 is minus 3.2 over, I believe, omega naught, omega D. Okay, omega D is 0.89. It's gonna be minus 1.62. Whoa. Now we just plug it in our equation and we have it complete. Plug it in right here, that equation right here. We have VL a T gonna be D1, and now D1 is negative 3.2 rho cosine omega D. Omega D is 0.89 T plus D2. D2 is also minus a negative number, minus 1.62 V psi 0.89 T. Everything times E to the negative alpha, which is negative 0.45 T plus V out at infinity is 3.2 rho. You can do a little bit algebra to bring it to the front and make it look prettier. I like it, put a positive number in the front first. So I factor out negative 1. I'm gonna have 3.2 cosine 0.89 T plus 1.62 sine 0.89 T. Everything E to the negative 45 T. Yeah, I should put a rho right here. Thank you so much for watching. Bye.